The aroma of fermented urine and decomposing organic matter was not just a byproduct of urban misery in the cities of the 17th century. It was the smell of military power. Men known as saltpeters turned over the soil of stables and public latrines, scraping the whitish crusts that formed on stone walls and compacted earth. That acidic efflorescence, born from the nitrogen of human and animal waste, was saltpeter, the oxidizer that would allow sulfur and charcoal to burn with devastating fury. Without this extract from filth, European monarchies would be incapable of projecting force beyond their borders, turning waste collection into one of the most strategic and repulsive industries of the pre-industrial era. Understanding the brutal mechanics behind these processes is what defines this channel. If you value this raw perspective of history, subscribe so you don't miss the upcoming technical excavations. The purification process required an almost alchemical patience and a total disregard for sensory comfort. The collected lands were deposited in large wooden tubs where water was filtered through layers of wood ash to convert calcium nitrate into potassium nitrate. The resulting liquid, a dark and dense brine, boiled for days in copper cauldrons under a constant fire that kept the workshops at a stifling temperature. The master saltpeter watched the formation of crystals with trained eyes, knowing that any remaining organic impurity would render the gunpowder unstable, capable of failing at the moment of firing, or worse, detonating prematurely during storage. When the potassium nitrate crystals finally emerged white and cold from the solution, they represented the most expensive and volatile component of the explosive triad. Mixed with yellow sulfur extracted from volcanic rocks and finely ground willow charcoal, they formed what was called meal powder. It was a fine powder, so volatile that a simple spark from a boot nail against the stone could pulverize the workshop roof. This primitive mixture was the technological heart of war, but its unstable nature and the tendency of its components to separate by weight during transport in carriages created a logistical nightmare that required an urgent mechanical solution. The meal powder had a fatal flaw that often cost the lives of gunners and musketeers on the battlefields of the 30 Years' War. Due to the difference in density between saltpeter, sulfur, and charcoal, the constant vibration of military marches caused the ingredients to settle in distinct layers within the oak barrels. At the bottom lay the heavy saltpeter. At the top, the light charcoal. When the soldier loaded his weapon, the resulting mixture was unbalanced, leading to a weak shot that barely propelled the lead, or in cases of concentrated excess saltpeter, an explosion that shattered the iron barrel directly into the shooter's face. Beyond chemical separation, the fine dust of primitive gunpowder was an invisible agent of death inside fortifications and in the holds of ships of the line. Any handling generated a cloud of microscopic particles floating in the air, turning enclosed spaces into vacuum chambers ready for ignition. The static electricity accumulated in woolen clothes or the heat from a poorly shielded tallow lantern was enough to trigger a chain reaction. The technical challenge was not just to create an explosion, but to tame the speed of that combustion, ensuring that the fire spread evenly and controlled among the components of the mixture. The solution came through granulation, or the process of turning the dust into small solid lumps. By compacting the wet mixture into blocks and then breaking them into grains of specific sizes, 17th century technicians created air spaces between each particle. This interstitial void allowed the ignition flame to travel instantly throughout the charge, burning everything at once instead of just the surface. The grain of gunpowder, now hardened and uniform, no longer separated with the sway of carriages and resisted ambient moisture much better, ensuring that the thunder of cannon fire was as predictable as the strike of a hammer. In order for the granulation to be possible, the dry mixture of saltpeter, sulfur, and charcoal needed to be transformed into a malleable mass. And it is here that practical chemistry met the more mundane fluids of the time. The use of pure water to moisten the gunpowder was problematic, as it evaporated too quickly and made the grains brittle, which turned back into dangerous dust in no time. The masters of gunpowder discovered that the addition of alcohol in the form of spirits or cheap wine and of fermented human urine created a much more resistant compound. The urine, rich in salts and urea, acted as a natural binding agent that sealed the pores of the charcoal and created a denser molecular structure after drying. The preparation ritual required the workers to handle this dark and sticky mass with bare hands or with large wooden shovels, avoiding any metal that could generate sparks. The smell was a nauseating mix of acrid alcohol, ammonia, and the metallic odor of sulfur, impregnating the skin and lungs of those operating in the mills. This sour gunpowder was pressed under enormous stone weights to expel the excess liquid, resulting in hard slabs known as press cakes. It was in these blocks that the chemistry of the field stabilized, allowing the latent energy of saltpeter to be trapped in a physical form capable of withstanding months of travel across the oceans. The preference for urine from men who consumed large quantities of wine or beer was not just a workshop superstition, but a technical observation about the purity of the residue. It was believed that the salts resulting from this specific consumption improved the ignition of the final product. Once the gunpowder cake was dry and hardened, it passed through perforated leather screens where it was broken into different calibers, coarse grains for siege cannons and fine grains for dueling pistols. This corned gunpowder process not only saved the treasuries of European crowns by avoiding waste, but it also ushered in an era where chemistry was measured by the efficiency of destruction. The sound that dominated the valleys where the gunpowder factories were installed was not that of smooth gears, but the rhythmic and heavy pounding of wooden pestles against stone mortars. These mills, often driven by the hydraulic force of diverted rivers, operated in a state of constant tension where heat was the absolute enemy. Each blow of the pestle on the damp mixture of saltpeter and sulfur generated friction, and if the mixture dried just a little beyond the critical point, the mechanical energy would turn into a sympathetic detonation. The sudden silence of a mill was often the prelude to disaster. If the rhythm stopped, the accumulated heat could find no escape, resulting in a crater where a production line once existed. The architecture of these facilities reflected the necessary paranoia for technical survival in the pre-industrial age. The walls were built with solid stones 2 meters thick, but the roofs were made of straw or light wood, designed to be blown upwards in case of an explosion, directing the force of the vacuum to the sky and preserving the foundations. The workers moved with felt slippers to avoid the slightest friction between leather and the residue-infested ground. The black powder covered every surface, turning men into living shadows inhaling particles of sulfur and charcoal. A pulmonary sacrifice in the name of a production that required 24 hours of vigilance so that the mass never reached ignition temperature. The final compression of the granulated gunpowder was the moment of greatest risk, where the mass transitioned from a malleable state to a rock-like consistency. Gigantic screw presses, operated by men pushing long wooden beams, applied tons of pressure on the gunpowder blocks. This process expelled the last microscopic air bubbles, ensuring that the final grain had the density of a mineral. Without this extreme compaction, the gunpowder would burn too quickly, turning the cannon into a grenade that would explode in the artillery's lap. The success of the operation was measured by the glassy sheen of the broken block surface, a sign that the components were fused into a solid and relentless unit. In the 18th century, the wealth of a nation was not measured merely by the reserves of gold in its banks, but by the capacity to guarantee the supply of potassium nitrate. The control of trade routes that brought saltpeter from the plains of India or Egypt became the central axis of British and French foreign policy. While domestic production depended on scraping filthy walls, the import of high-purity crystals from the East allowed for the creation of gunpowder. With a potency 30% greater, This chemical advantage meant that the ships of the Royal Navy could use less gunpowder to reach greater distances, enabling them to carry more ammunition and less dead weight in their hold. The economy of gunpowder was a financial black hole that consumed entire budgets of absolutist states. The cost of maintaining stable gunpowder depots was astronomical, as saltpeter is highly hygroscopic, absorbing moisture from the air and ruining the grain unless stored in perfectly sealed oak barrels and kept away from damp ground. Empires that could not master the logistics of granulation and storage saw their war fleets become useless in tropical climates, where poorly processed gunpowder reverted to a black and inert sludge in just a few weeks. Chemistry, therefore, dictated the geography of colonial domination. The state monopoly on production was the norm, with royal inspectors visiting private mills to ensure that the ratio of 75% saltpeter, 15 of coal, and 10 of sulfur was rigorously maintained. Any attempt to adulterate the mixture with cheap substances to increase profit was considered high treason, punishable by death. This occurred because the standardization of grain allowed military engineers to calculate, for the first time in history, the exact trajectory of a projectile. Gunpowder ceased to be an unstable alchemical ingredient to become a precision industrial commodity, the first mass chemical product that required global quality control. The final transition to granular gunpowder permanently changed the design of European metallurgy. Before granulation, cannons needed to be short and extremely heavy to avoid explosion from the irregular shock of flour-like gunpowder. With the advent of uniform grains, the burning became progressive. The fire traveled through the spaces between the grains, generating an expansion of gases that continued to push the bullet while it was still inside the barrel. This allowed for the creation of longer and more precise bronze and iron barrels, capable of converting chemical energy into sufficient kinetic speed to penetrate the walls of medieval castles that had stood for centuries. The plate armor of the knight, which for 400 years represented the pinnacle of individual protection, became obsolete in the face of the impact of a projectile propelled by granular gunpowder with alcohol and urine. The impact of an 18-millimeter musket ball, fired with a load of high-density grains, possessed an energy that tempered steel could no longer dissipate. The battlefield became a place of dense and acrid smoke, where the tactics of mass infantry were the only logical response to a weapon that ignored individual fencing skill and aristocratic lineage. Death became impersonal, mechanical, and above all, chemical. At the end of the process, granular gunpowder represented the first great triumph of materials engineering over raw nature. By transforming human waste and volcanic minerals into a ballistic precision tool, the 18th century laid the groundwork for the chemical revolution that would follow. Corned powder was not merely an explosive. It was the catalyst that forced the development of machine tools, scientific testing methods, and a global logistics infrastructure. When the last cannon of the Napoleonic era fell silent, it did so using technology that was born in the muck of latrines, but ultimately outlined the borders of the modern world. Dominance over black powder was not only a military victory, but the hallmark of an era where civilization learned to extract power from molecular chaos to shape geopolitics. Each cannon shot in the 18th century was the echo of a process that linked the chemistry of latrines to the precision of metallurgy, proving that economic history is written with both blood and sulfur. If you seek to understand the raw gears that built the modern world, without filters or romanticism, your journey continues here. Sign up now to secure access to the next technical analysis.